Well, thanks so much, Randy. And yes, we are hearing a lot, and I think this is kind of an extension of some of the message that Chris was discussing in his presentation, in terms of through faults. And we're going to talk a lot about through faults today. The first thing you'll see in my presentation, I always put my bio in a presentation as such, not so much that you have to remember my professional history in the industry, but more so you have my email address and my telephone number there. And I invite any one of you at any time, if you have questions or anything comes up that you'd like some assistance with, feel free to reach out at any time. I know a lot of times when we do these presentations, you'll think to yourself, oh, why didn't I ask this question? And so that is always available to you directly through my email. So basically, when we talk about failure points in transformers, they're categorized in three separate areas. One would be mechanical failure, two is electrical failure, and then finally insulation failures. And these can be broken down in significantly different categories in terms of what has caused the failure. But today we're going to kind of focus on mechanical failures. And mechanical failures basically are described as the physical displacement or damage of parts within a transformer. And this can happen for several reasons, including but not limited to transportation, okay, which is why whenever you purchase a new transformer and before it leaves the factory, you want to get a benchmark on an SFRA and then compare that once it's ready to be commissioned as your footprint. Seismic activity, improper synchronizing on a GSU. But today, what we're going to focus on are through faults. So what Chris talked about really leads into this presentation quite well. So, power system faults, it can actually really cause some damages. You can see here in the illustration on the screen here, is something that we really need to be concerned with. And I will say that for the most part, this is something that a lot of people tend to overlook in terms of their protection scheme. I mean, we all know that protective relays have differential protection for internal faults in the transformer. You have other types of protective elements that deal with things like volts per hertz conditions or overexcitation, especially for GSUs, and various overcurrent elements, some thermal protection that will take the transformer offline if it's overheated. But you can see that through faults really do create a bit of a concern when it comes to mechanical failure. So let's talk about why this can be so problematic. Well, let's assume, of course, that you have a transformer out in a transmission system, okay, or even in distribution. And that transmission line or that distribution circuit has its own protection in the form of overcurrent protection, or in a transmission line, you have distance protection or line differential protection in the event of a fault, okay, that would happen out in the system. But with a transformer, okay, it's not really expected to respond to a through fault. Okay, there's nothing that protects internally in the protection system of the transformer that protects it in the event of a through fault. If you have a fault down in the transmission system, okay, and by the time your distance relay or your differential relay takes that system offline, the through faults are already gone through that transformer. Okay, so this presents a bit of a problem. And to really understand how through faults occur and what can happen, is that we have to look at how differential protection works. So if you have a fault on on either side of the transformer outside the protective zone of the CTs, that's considered a through fault. Now, differential protection will only sense the faults occurring inside the range of those CTs. Okay, as we know, if you have a fault in the internal windings of the transformer, okay, your current starts to go towards the fault, and you have a difference in current between what goes in and what comes out, and that's considered a differential fault. Now, it's kind of funny when we consider transformer protective relaying, because some of your relays are reactive and some of them are proactive. A a differential relay on a transformer would be considered more to be reactive. Okay, if you have a differential relay trip, that means you've already got an issue inside the transformer. You're not really protecting anything. Now you will protect it against catastrophic failure or a serious failure that would result in a fire or an explosion. But for the most part, if your differential relay trips from a true fault within the transformer itself, you've already got that problem. Now, there are protective elements, such as volts per hertz or thermal protection on that transformer that will keep it from becoming damaged due to certain system conditions, but not through faults. Okay. Now, transformer throughout the power system experience through faults in terms of magnitude, duration, and frequency. And the recording capability of those transformer protective relays actually allow for monitoring and recording of through fault current, as do a lot of new modern transformer monitoring systems will monitor through faults and record these through faults for you. Okay, now it's interesting that I brought up this subject because a number of years ago I was talking to a relay engineer from Schweitzer, and his specialty was transformer protection. And I mentioned to him, I said, all your modern differential relays, your modern transformer protective relays have through faults monitors in them. And he said, yeah, that's true, Drew. He says, but I have to tell you that very few people actually enable the through fault monitoring system in the relay itself. So this can be a real problem because you don't know what you don't know. And mechanical failure in a transformer can be through faults don't necessarily damage the transformer instantaneously or right away. It could be a series of through faults that over time will lead to excessive mechanical failure. Now, one of the things that's important to understand is that a lot of the potential damage to the transformer has to do with how that core is designed. Through faults actually are more damaging to a core form rather than a shell form, because the shell form designs have multiple current channels and can withstand a through fault better than a core form. However, that doesn't mean that a shell form is not going to sustain damage from a through fault. It's just that it can withstand a little bit better than the core form in and of itself. So basically, how do we monitor through faults? Well, basically, it's an I²T value for each phase, and it compares a threshold in terms of how much through fault has gone. And here, what you'll see in this diagram is kind of the logic setting in a through fault monitor from a protective relay or a monitoring system. And we're going to record these values, and really there's a lot of information that you can gain from looking at your through fault monitoring data. For instance, this happens also, it's not just in high voltage situations, but in distribution systems, distribution substations. If you have a large number of through faults, maybe not to the magnitude that would do any damage, but that could indicate that you may have some maintenance to do out in the distribution circuit in terms of tree trimming or things like that. So this is an important information, no matter what the magnitude or the situation can be. So over time, the recorded values provide this important information that ought to be looked at on a regular basis. So excessive through fault occurrences within a given period, can again indicate that, you need to take a look at what that cause might be. But this is a sample report, and this comes out of a Schweitzer relay right here. And you'll notice that you'll see a number of different things. You'll see the date and the time of the through fault when it occurred, how long, okay, the maximum through fault was sustained through the transformer itself, the magnitude, and how many times it's happened, date and time stamp. And really, this is important information to know, and can guide you to, having a suspect as to whether or not you have incurred some mechanical damage in the transformer itself. So power transformers, they consist of a set of windings around a magnetic core, and these windings are insulated from each other. The transformer windings and the core are subjected to certain forces during operation. And these forces can be expansion and contraction caused by thermal cycling, excessive vibration caused by flux in the core changing direction, localized heating caused by eddy currents in parts of the winding, magnetic flux, thermal heating caused by overloading, okay, can also, damage the transformer. But what we're going to look at is the impact forces caused by through fault currents. Okay, now, how do we set a through fault monitor?
The restriction doesn't.
Okay, if we could make sure our microphones are on mute. Thank you. So IEEE and ANSI standards provide operating limits for power transformers that are, they always had these in terms of thermal limits. Okay, we always, from the manufacturer knew what the thermal capabilities could withstand in a power transformer. But it's only a little bit more recent that we looked at the mechanical effects of what those capabilities were in terms of a through fault. So basically, power transformer through faults produce physical forces that can cause excessive compression in the windings, insulation wear, friction-induced displacement. And the way you would monitor, or the way you would set a through fault monitor, has mostly to do with the category or the rating of the transformer in terms of what it can withstand. And we all know that your transformers come in different categories. This is category 1 through 4, and it has to do with the kVA rating, both single phase and 3-phase. So when we look at setting a through fault monitor, we want to actually be able to provide more comprehensive representation of the long-term effects on these transformers. And each category of transformer actually has its own limitation in terms of the maximum current through the transformer. And if you are going to set your through fault monitor in terms of when you wanted to be alerted to the through faults, you have to kind of understand the short circuit impedance and the system impedance. And there are certain calculations that you can go through, and this one actually shows you a representation of the transformer rating, the secondary voltage, the percentage impedance, and that will calculate your transformer secondary current in terms of amps, in terms of what that transformer can withstand. So if we look at a combination of different types of curves, you'll see on the vertical axis, you'll see the time and the duration of the through fault. And then on the horizontal axis, you will see the times base current in terms of the magnitude of the fault. So each category has a different setting limit in terms of the mechanical force. And if you want to really dig deep into it, C57109 is a guide for liquid immersed transformers in terms of through fault current duration. Okay, so there are standards and recommendations in terms of how to set a through fault monitor. Okay, so what's going to happen here, and this is an example of a protective relay, and it's transformer monitoring characteristic curve. And basically what we're looking here is a number of things. Again, we're looking at recording the magnitude, we're looking at recording the the duration of the through fault, and the number of occurrences. So you can set, alarms based on the number of through faults that have occurred, and based on the magnitude, and based on the duration. And basically, when you put let's say you're swapping out one relay to the other. Well, you'll want to take and preload the data from the older relay, if you have data, to continuously count the number of through faults that have occurred on that system. So this is just kind of an example of what you see in terms of setting a through fault monitor in a protective relay. Well, what happens when we see a through fault condition? Well, there's a certain number of diagnostic tests that we want to focus on to determine whether or not we've had some mechanical damage in the windings of the transformer itself. Now, of course, the most thorough way to detect a mechanical failure is with your SFRA, your sweep frequency response analysis, but also your leakage reactance. Both three-phase equivalent and per-phase tests are fairly important as well. Now, let's think about how we do and what we do when we perform dielectric testing or electrical testing on a transformer. Maybe you're doing it annually or every other year. If you do not have any type of through fault monitoring, and you really have no idea how many through faults have occurred or what the magnitude of those through faults are, then I would suspect that when you go out and you do your dielectric testing, you want to include a leakage reactance test. That's really should be part of your testing process if you don't have any through fault recording on there, because basically by comparing the impedance that we're measuring, you'll get a pretty good indication as to whether or not you may have some mechanical damage. And of course, if that's showing an excessive level, then you'll probably want to jump into your SFRA. But SFRA, of course, is very important in terms of determining the extent of any potential mechanical failures. And this is why when we order a new transformer from the factory, we always have them, should have the factory do a footprint, okay, with an SFRA, and compare that trace to when we actually commission the transformer itself. So let's take a look at a couple of industry guides that can help you. C57109. This is the application and interpretation of SFRA for transformers, and this has been in a revision mode and is just about complete. A good friend of mine, Charles Sweetser from Omicron, is actually the chairman of this committee, and he's done a really good job in terms of how to conduct the test, how to wire the test, and some really updated information that goes along with this guide. For other tests, of course, you've got C57152, which is a diagnostic field testing of power transformers, regulators, and reactors. So these are two good industry guides to help you in terms of mechanical failure in the transformers. So let's first talk about SFRA. Well, this is a method to evaluate the mechanical integrity of the core and the windings and the clamping structures. And like Chris was saying, a through fault can actually cause core movements, faulty core grounds, winding deformation, winding displacements, partial winding collapse, hoop buckling. You can see some pretty good examples of what mechanical failures look like internally in the windings of the transformer. And basically what we're doing is SFRA, and in case you're not familiar with it, is an offline low voltage test, and non-destructive, of course, where we're actually going to do a frequency sweep and record the decibels and plot this out, both three-phase and single phase. And it's been around. This type of test has been around a long time, and it's kind of like having a fingerprint. And this is why having a baseline is so important. Now, if you don't have a baseline of an SFRA test, you can always compare the phases to one another. and compare the primary and the secondary windings. But really, the fingerprint is very, very important in terms of getting a good, accurate assessment of any potential mechanical failure. So we have an input signal in terms of a sine wave with variable frequency, and then we're measuring measuring and plotting the magnitude and the phase angle. Okay, and looking at the difference in the signal from its original to the one that we're going to be taking. Fairly easy to wire and perform. Okay, the thing of it is with SFRA is that you have to do a number of dielectric tests depending on the winding configuration of the transformer. For instance, here, and again, this comes from C57149. These are the recommended wiring configurations and tests that you do on a delta Y configuration on a two-winding transformer. And you can see there's a number of tests: high voltage open circuit, low voltage open circuit, and then short circuit tests. And this chart right here, and this got expanded upon and refined in the new revision of C57149. But this kind of gives you an indication on what you have to measure, what's shorted, what's grounded, and then what type of test it is, because what we're really doing is focusing on where that potential damage is located in the transformer itself. It's kind of like a chest x-ray. You're going from front to back, from back to front, side to side, on both sides. It's kind of the same thing. We're really trying to hone in on where that possible or potential mechanical failure could be. So this is kind of an example of what these traces look like. And you have three groups of traces that typically come from a typical SFR measurement. And the three groups are known as a high voltage open circuit, a low voltage open circuit, and high voltage to low voltage short circuit response. And you would compare the results to the original trace to see where and if there are any mechanical failures as well. Now, depending on the range, okay, and this is really what is important here, is that if you have core damage, okay, this will be in the lower range, and then in your mid range you have an interaction between the windings, and then on the high end you have the winding structures themselves. So you get a lot of good information. The good news is, and I can remember back in the early days of SFRA, where field technicians would look at the results and kind of throw up their hands and say, what am I looking at, and have to refer back to the folks at Doble or who Mega or whatever, and say, what am I looking at? Can you help me interpret this test? The good news is that the software associated with SFRA equipment is now a lot better in terms of pointing out and determining any differences in the test results themselves. So basically, when we talk about through faults and we talk about the possible considerations that we see, experience has shown us that winding movements caused by high through faults in a transformer is generally associated with the low voltage winding in the form of radial deformation. And the diagnostic focus will be given to the low voltage open circuit and high voltage to low voltage short circuit test results. And again, this is all highlighted in the guide for SFRA testing. So you get some really good information in terms of where the potential damage might be located. And again, the software that's associated with this equipment will give you a good information in terms of whether you have a failed test or whether you have a passing test when you compare the traces from the original. Okay, now another test that I kind of want to discuss, and that is a leakage reactance, and we also refer to this as a short circuit impedance test. And basically, what we're doing is we're going to short circuit our low voltage windings. We're going to put in anywhere from 0.5 to 1% of the rated current at 60 hertz, and then apply about a 280 volts. And then what we're measuring is the impedance of the windings of the transformer. And there's two separate tests that we want to run. One is called the three-phase equivalent, okay, because you only have basically a single-phase source, but we want to calculate a three-phase equivalent, and then the per phase. Okay, now it's an AC test, which is performed to detect mechanical winding movement and or deformation within a power transformer. And the leakage reactance measurement, this directly corresponds with leakage flux. And think about it this way. Think of you've got an open trough running downhill, and you've got water running through that trough. Well, somebody comes along and takes a big stone and puts it in the middle of the trough, and the next thing you know, you've got water spilling over the sides. Well, this is kind of the same thing that we're looking for in terms of leakage flux, which is going to create your impedance that's used to limit the short circuit current. So leakage flux creates reactive magnetic energy, and this behaves like an inductor in series in the primary and the secondary circuits. The impedance can be easily measured, analyzed, and trended. And this is kind of, a diagram about how, the flux moves through the core and the windings of the transformer. And this is basically what we are going to measure. Now, as everybody knows, okay, when you look at the nameplate of a transformer, it should have the impedance measurement of the transformer stamped on the nameplate. Okay, now the first test, of course, is going to be your three-phase equivalent. And basically what that does is that takes your three measurements and then calculates that as to what the three-phase impedance is that is being measured. Now, with that being said, that measurement should be plus or minus 3%, okay, in terms of industry standard to what is stamped on that nameplate. If it's not, you have a potential mechanical issue in the windings of the transformer itself. So you can see right here, and whenever you're going out to test a transformer, and people in the field, I really, whether you're a relay guy or you're a test technician on power transfers, you need to become intimately familiar with the nameplate of that transformer. This helps you, not only does it help you properly set your protective relay system, but it also helps you to properly configure the tests that you're going to be running on that transformer itself. You'd be surprised how many people go out and start to do power factor testing on a transformer, and then all of a sudden either myself or one of our technicians gets a call and say, how come I'm getting a negative power factor measurement? Well, you don't have your there's no such thing as negative power factor. You either have your bad connection to the bushings of the transformer, or you have it configured wrong and you're not getting a true measurement. So it's really, really important to become familiar with the nameplate of the transformer in terms of how it's configured, high side voltage, low side voltage, the ratios. It's all there, and very important in terms of diagnosing. Now, in the terms of doing a three-phase equivalent, again, this impedance value that's on the nameplate should be within plus or minus 3% of what you're measuring during your leakage reactance test. And here's an example, okay, of a three-phase equivalent, okay, where we've done our measurements, and then we've calculated the delta in the impedance measurement. In this case, well within tolerance, it's a 2.04%. And of course, you can see it's a two-winding delta Y connected transformer. A couple of things that are important when you do a leakage reactance test: you want to make sure the transformer tank and core are solidly grounded. And this is a big mistake that I see people make every once in a while, and you have to make sure to include both the test instrument and the power source that are grounded as well to the common ground node. I know a lot of people go out in the field and they use generators to run their test equipment. and some of those don't have a proper grounding, and this will cause bad results or could even damage your test equipment. So this is something that's very important whenever you go out and test a transformer. Then you want to isolate the transformer terminals. You want to remove the external connections in the buswork for your high and your low side bushings and XO, and then isolate H1, H2, and H3, making sure they're not connected together, which is different from some of the other tests that you perform. And just like any other test, it's all temperature and humidity sensitive, so you want to record this information. And one of the things that I also always advocate when you're doing tests like this on a transformer is that you want to use a good solid, at least a number 4 gauge bare copper conductor and C clamps when you're connecting your test leads and when you're shorting bushings. Always very, very important. So this is a short circuit impedance test, and you want to short X1, X2, and X3, but do not include the XO. You want to keep the ground on the XO. And then identify the impedance, base power, and base voltage from the nameplate, and verify that the de-energized tap changer and on-load tap changer are in the normal rated tap position. Because if it's not, then your three-phase equivalent measurement won't be comparable to the nameplate. Okay, and just a few notes right here. You'll have a 4-wire Kelvin connection that you're going to apply. And then you want to make sure that you have enough current going through to establish either a 30, let's say between 30 and 100 volt AC drop across the primary windings. And this is important in terms of being able to get a good measurement, just like you would if you were doing a winding resistance test. Okay, now, basically, here's your connections for a leakage reactance test. Okay, in terms of both the 3-phase equivalent and your connections for a per phase test. And this diagram right here will show you where to connect your leads, what to short, and what to measure. So you can see in the 3-phase equivalent for all 3 of these tests, we're going to short all your low side bushings, ground the XO, and then measure H1, H3, H2 to H1, and then H3 to H2. On your per phase test, it's a little bit different. Okay, we're going to float X2 and X3, and then short X1 and XO and measure H1 to H3. So the thing you want to do and the thing you want to be careful about when you're doing these tests is making sure that your connections are correct according to the table here. Okay, so what are our expected results? Well, as I said before, the purpose of the 3-phase equivalent test is to produce test results to compare with the factory settings. And again, your impedance should be plus or minus 3%. Now, on a per phase test, okay, you want to make sure that each phase, each one of those 3 phases that you're doing are all within 3% of each other. Because you can get, we'll see this a little later on in the case study, you can end up with a 3-phase equivalent that is within plus or minus 3%. However, you could have one of those 3 phases out of that 3% range. So both these types of tests are important. All right, so let's take a quick look at a case study here. We're testing a transformer that had an obvious mechanical failure. It experienced a significant number of through faults in a fairly short period of time. So after these reported through fault alarms, finally the differential relay tripped. And unfortunately, that's what happens. If these through faults continue to happen and they're high enough. So we sent a substation maintenance crew out to investigate. And of course, the very first thing you always do when you go to investigate an issue as such is you want to do your DGA. And you'll see here, and DGA is, of course, we keep a historical record of what those measurements have been over time during our maintenance testing. And you'll notice here the acetylene went from 0 all the way up to 21. Now, that's a serious indication that we have a problem right off the bat. So the next test was the leakage reactance test, and here's what the results told us. And you can see here that our three-phase equivalent, okay, and again, this is what I was alluding to, we had less than 3% delta, okay, on the three-phase equivalent. Well, that, of course, that test passed, okay. However, if we look at the per phase, okay, we had a delta of 9.62% on one of the phases, on phase B. Okay. And this is typical of an open circuit. All right. So whenever we try and determine what's going on with a transformer, it's like a puzzle. You want to look at a number of different tests. You want to look at a number of different conditions in your reports and try and piece it all together. Okay. Obviously, because of the through fault monitoring system recording so many through faults, the differential relay tripping, the the DGA coming out with a high amount of acetylene, we obviously know we have a serious problem with this transformer. We did a DC winding resistance test, and that also confirmed an open circuit. But what's interesting here is that when we did that, phases A and C, they produced an expected result in terms of the winding resistance itself. So we've kind of honed in. Well, we go a little bit further and we look at our SFRA test, and this is really the tell-all right here. They indicate a high impedance fault on phase B of the low voltage winding. And remember what I mentioned before is both the low voltage open circuit and the high voltage to low voltage short circuit test provides this evidence. So this trace right here clearly illustrates a failure mode on phase B. Okay, so this is also pretty interesting. In this case study, again, 50 MVA transformer, configured delta Y, DY1, trip from service. The other telltale was that it had oil appeared to be leaking from the low voltage de-energized tap changer. We put a standard test protocol, which included the SFRA and leakage reactance, but you'll also notice here on the power factor test, it wouldn't even run on the low side at 10 kV. So basically they lowered the voltage down to 7 kV, and the power factor was almost 50%, which is just outrageously bad. So this was clearly unacceptable. So basically, when they tore the transformer down, you could see that the dramatic effects of the mechanical failure. Now, let me just say this in terms of through fault monitoring and when to run tests and what tests to run. If you have a through fault monitor, okay, on your system, either in the protective relay or from your monitoring system, and you have no signs of any through faults that have really happened that exceed that threshold or that the relay has recorded, okay, I would probably tell you that that leakage reactance or SFRA would not be a necessary test when you go out to do your routine testing. If you don't have any indication of a through fault because you don't have a monitoring system, maybe you've got old BDDs and HU relays and discrete electromechanical still protecting that transformer, and they are still out there, and no monitoring system, you have no clue as to whether or not that you've had through faults or through fault conditions. I would say that a leakage reactance should be part of your routine testing. It doesn't take that much longer to run, and most of your power factor test sets have that capability, either inclusive in the test set or as an accessory to the test set or as part of your winding resistance test set, like a Raytech. Okay, so I would strongly suggest that you include leakage reactance if you have no clue as to whether or not you've had through faults. If your leakage reactance is not within its limits, certainly, or you have experienced through faults through your monitoring system, I would say take the take the leakage reactance test one step further and perform an SFRA, because that really is the all tell as to whether or not you've got some mechanical damage to the transformer. And that mechanical damage may not result in an internal fault right off the bat, but it's something that should be investigated if you're seeing any kind of bad results. So with that being said, I will take questions, Randy, if anybody has some coming up.
Yeah, thanks very much, Drew. Good presentation, very comprehensive. Okay, let's see. Does the guide to SFRA testing address rectifier duty transformers?
I don't believe it does. And if Chris is still on the line, he may know a little bit better about that. And I have not been on that working group. But if who's ever asking the question wants to send me an email, I will find out for you.
Yeah, I'm going to in a minute. I'm going to put everybody's the four speakers today. I'll put into the chat box the email addresses for everybody, and you can ask Drew that question.
Sure.
And you can. Who was it was asking? It was Kyle
Hi,
Pataki.
Kyle.
Kyle Pataki. You know Kyle?
Kyle, good question. Yeah,
Okay.
just send me your email address and I'll do a little research on it for you.
Okay, next up, is there any value to SFRA test at frequencies below 60 hertz, i.e. saturation curve, geomagnetic response, etc.?
Oh, yes, absolutely. In fact, your SFRA tests go down quite a bit lower than 60 hertz. And some of them, I mean, depending on the test set that you're using, go down lower than others, but that's more specmanship than anything else. But yes, if you're talking about the test frequency of the actual test itself, yes, it does go down quite a bit lower.
Okay, next question. Are your recommendations applicable to cast coil XFMR?
Cast coil transformers, yes.
Yeah.
Yep, by all means.
Okay. All right.